Section 3.1, Quadratic Functions. The graph of any quadratic function is called a parabola. Parabolas are shaped like bowls or inverted bowls, as shown here. The vertex or turning point of the parabola is the lowest point on the graph when it opens upward, and it's the highest point on the graph when it opens downward. Parabolas are symmetric with respect to a vertical line that passes through the vertex. This vertical line is called the axis of symmetry. The axis of symmetry divides the parabola in half. Consider the parabola defined by the quadratic function f of x equals ax squared plus bx plus c. The x-coordinate of the vertex is negative b over 2a. The y-coordinate is then found by substituting that x-coordinate, negative b over 2a, into the parabola's equation and evaluating the function at this value of x. So the parabola's vertex is negative b over 2a, comma, f of negative b over 2a. And the axis of symmetry is the vertical line with the equation x equals negative b over 2a. To graph a quadratic function, we'll first determine whether the parabola opens upward or downward. If a is positive, it opens up. If a is negative, it opens down. Next, we'll determine the vertex of the parabola, where the vertex has an x value of negative b over 2a and a y value, which is the function's value at that x value. The third step is to find any x-intercepts by solving f of x equals 0. The real solutions of ax squared plus bx plus c equals 0 are the x-intercepts. Note that solving f of x equals 0 involves the quadratic formula, which can be somewhat cumbersome. So sometimes, if they're not specifically asking for us to find the x-intercepts, we'll find other points instead by substituting x values that are on either side of the vertex. Step 4 is to find the y-intercept by computing f of 0. Because f of 0 always equals c, the constant term, the y-intercept is always c, and the parabola passes through the point 0, c. Step 5 is to plot the intercepts, the vertex, and any other points that we found, and we'll connect these points with a smooth curve. Example 1. Graph the quadratic function f of x equals negative x squared plus 4x plus 1, then use the graph to identify the function's domain and range. Step 1 is to determine how the parabola opens. Since a is negative 1, that means it's less than 0, so the parabola opens downward. Step 2 is to find the vertex. The x-coordinate is negative b over 2a, so we take our values for a and b and substitute them in, and that gives us an x value of 2. We continue to find the vertex by taking that x value of 2, but now we need to find the corresponding y value. So we substitute in the x equals 2, and that works out to a value of 5. So the coordinates of the vertex are 2, 5. For step 3, we'll find the x-intercepts by solving f of x equals 0. So we take our function, replace f of x with 0, and then we use our quadratic formula. We simplify, and this plus or minus means this leads to two different values. We use our calculator to approximate it when there's a plus, and we use our calculator again to approximate it when there's a minus. So our x-intercepts are negative 0.2 and 4.2. You may recall that sometimes we leave our answers in simplest radical form, but since we're taking these to graph paper, having the approximate value will allow us to plot these points. I mentioned that there was an alternative step 3 that might be easier to find additional points. Since the vertex had an x value of 2, we can go an equal distance on either side and substitute in a 1 and a 3. We take our function, we substitute in 1, and we simplify, and that gives us a 4. We repeat that process substituting in a 3, that also gives us a 4, so that means we get the points 1, 4, and 3, 4 on our parabola. Step 4 is to find the y-intercept by computing f of 0. When we substitute in a 0, the first and second term drops out, we just get the constant term. So the y-intercept is 1, so that means that the point 0, 1 is on our parabola. Step 5 is to graph the parabola. So we can take our x-intercepts and plot those. We can plot the two alternative points that we found. Our intercept was the point 0, 1. The vertex is 2, 5. and then we take a smooth curve and draw it through all those points. The axis of symmetry is 2, so we draw that in. We need to identify the function's domain and range. The domain are the possible x values, which are everything from negative infinity to positive infinity, so that's our domain. The graph has a maximum value of 5 and then goes down infinitely from there. So the range is negative infinity comma 5. Notice we always put a parentheses next to infinity or negative infinity. The 5 gets a bracket because it's included on the graph. When working with quadratic functions, we're often asked to find minimums and maximums. This will occur at the vertex, so when a is greater than 0, the function will have a minimum value that occurs at x equals negative b over 2a, and the minimum value will be the function's value at that negative b over 2a. When a is less than 0, the parabola opens downward, so the function will have a maximum value that again occurs at x equals negative b over 2a, and that maximum value will be the function's value at negative b over 2a. In each case, the value of x gives the location of the maximum or minimum, and the value of y, or f equals negative b over 2a, is the minimum or maximum value. Example 2. Consider the quadratic function f of x equals 4x squared minus 16x plus 1,000. Part A, we want to determine without graphing whether the function has a minimum value or a maximum value. Then we'll find that minimum or maximum value and determine where it occurs. We'll find the axis of symmetry, and we'll identify the function's domain and range without graphing. For part A, we want to determine whether the function has a minimum or maximum value. Note that a is 4, and since a is greater than 0, the graph opens upward, so therefore the function has a minimum value. For part B, we want to find that minimum or maximum value, and we know that we are now looking for a minimum value. To determine where it occurs, we take our values for a and b and substitute them in for negative b over 2a. We substitute and simplify, and that gives us a value of 2. So the minimum value occurs at 2. Then we find f of 2 by substitution, and that tells us that the minimum value of f is 984. Part C is to find the axis of symmetry. Recall that in part B we found the vertex, so we found that x equals 2. So this also tells us that the axis of symmetry is the vertical line with the equation x equals 2. When stating the axis of symmetry, you must include the x equals. Part D, identify the function's domain and range without graphing. Like all quadratic functions, the domain is all reals. Then we found that the vertex was 2, 984, and since a is positive, the function opens up and has a minimum, and therefore the range of the function starts at 984 and goes up to positive infinity. Next, we're going to consider parabolas defined by the equation x equals ay squared plus by plus c. Such parabolas open to the left or to the right, and thus they are not functions. We'll see that many of their characteristics will be the inverse of quadratic functions. The y-coordinate of the vertex will be negative b over 2a. Then we'll find the x-coordinate from the y value by substituting that negative b over 2a value. And the axis of symmetry will be a horizontal line of the form y equals negative b over 2a. To graph a parabola in this form, first we'll determine whether the parabola opens right or left. If a is positive, it opens to the right. If a is negative, it opens to the left. Next, we determine the vertex of the parabola. Then we find any y-intercepts by solving the quadratic ay squared plus by plus c equals 0. We find the x-intercept, which will always be c comma 0. And then we plot the points that we found plus any additional points, and we connect them with a smooth curve. Example 3. Graph the parabola x equals negative 4y squared plus 8y minus 5, and use the graph to identify the domain and range. We start by determining how the parabola opens. Since a is negative 4, that's less than 0, so the parabola opens to the left. Next, we'll find the vertex. We use y equals negative b over 2a. We take a and b and substitute them in, and that simplifies to 1. Continuing, we found that y is 1. So we substitute that y in, and we find that x is -1. So the coordinates of the vertex are -1, 1. Step 3 is to find the y-intercepts by letting x equal 0 and solving for y using the quadratic formula. We substitute in the values for a, b, and c, and we simplify, and then we recognize that we have a negative under the radical, which means there are no y-intercepts. We could have avoided this algebra if we noticed that the vertex of -1, 1 is on the left of the y-axis and the parabola opens to the left, so therefore it will never make contact with the y-axis. Step 4 is to find the x-intercept by substituting y equals 0. We substitute the 0 in, and we get x equals -5, so that's our x-intercept, and the parabola passes through the point -5, 0. Step 5 is to graph the parabola. But with no y-intercepts, we should find some additional points. The coordinates of the vertex are -1, 1, so we can find points 1 unit below and 1 unit above the axis of symmetry, y equals 0 and y equals 2. We already found the point when y was 0, so now let's find the point when y is 2. We substitute it in, and it gives us a corresponding x value of -5, so we have the point -5, 2. And now we're ready to graph the parabola. We start with the x-intercept at -5, 0. We had no y-intercepts. The vertex is -1, 1. We had the point -5, 2. So we draw our smooth curve through it. We can plot our axis of symmetry at the horizontal line y equals 1. Our domain is -∞, -1. So that means the x values go from the negative x's all the way up, including -1. And finally, the range is all reals from -∞ to infinity.